So you are given matrix X, this like data, and then you want to solve this, right? Okay, X minus XAB for business norm. Okay, so last week we talked about A minus BC, right? Okay, so basically our focus is on the variable. So for this expression, these two are the variable. Okay, then you may say, oh no, they don't look like the same thing. Doesn't matter. Okay, it's the same. It's the same as you have a W here. Okay. So that means if this is the forbiddance norm, okay, you now should know how to expand it. It's a trace of the thing inside transpose, and then you expand the bracket and use those cyclic invariant. You can move this there and transpose, do all the stuff. You can write down an expression that's only on A or only on B, right? Okay, so now, because of time, let's say we focus on B. Okay, I don't care about this. So now we want to minimize this guy. Then we need this, right? So for the illustration, I just assume X is just some random matrix. Okay, R-A-N-D. Okay. So I need to know how big is this matrix. So I have a matrix X. This is M. Okay, and then this is N, right? Okay, this is X. Okay. So now I need to define M and N. I just randomly make a number. Let's say 20, and then this is 40. Okay, I just randomly make some number. Okay, then I MN. So this could give me what? A random matrix, 20 row, 40 column. Okay, I just run this. Yeah, how many column? Well, 40 column. How many row? You count. It should be 20. Okay, no. Okay, or you can look at this. Okay, see, 20 by 40. Okay, then what's next? Well, I need to find A and B such that this is small. So that means if I find A and B such that X subtract itself multiply AB, then my goal achieved, right? Here I didn't talk about the constraint on A and B because for 2 weeks ago we said that A needs some constraint, for example, larger than 0, column inside simplex, right? But let's say ignore those for a moment. So let's say I just want to find AB, and now I'm going to focus on B. Okay, so let's say I also know A. Okay, rank. Okay, also rank up. Okay, so N by, let's say, okay, N by R. Okay, R is a rank. Okay, let's say I have a R. Okay, R is a 3. Okay, let's say that's 3, and then so now I'm going to run this. Okay, so now I run everything like this. Okay, so I can have X and I have A. Okay, I can have XA, right? Now I have X times A. What I want is to find this question mark such that they're equal, right? And how do you solve this problem? Of course you say, oh, I assume this is I, but the problem is X is not square matrix, so this is wrong, right? And also, even if X is a square matrix, it's not necessarily invertible, right? It's possible that X is singular. That means eigenvalue or singular value of 0. Okay, so that means you need to solve this. I'm saying this because that means I'm trying to say the situation that you cannot use linear algebra to solve it. That's why you need to do optimization. Okay, because that's a general case. So now we try to what we want to both find B such that what? This is true, right? So such that X is this. This is true what? If and only if what? X minus XAB, the norm is small, right? So that means we just need to make sure this is small. Mathematically, it's what? Minimize. So I have some objective function. I call my objective function f, which is a function of b, okay? And then what? My subject is b. I just care about b. I don't care about a for a moment. F is just the norm between x minus x a b, okay? And then I have this, okay? For business norm, okay? And I put a half here. Okay, then you may ask, why you put a half here? The reason is that if I do differentiation, the 2 will come out, then it will cancel out with the half and it will disappear. And if I don't put a half here, when I do differentiation, the 2 will come out, I will get something 2, something. I don't want the 2. I just want the 2 to be gone. The purpose of this half is just to remove the 2. If I have a power 4 here, then I will put a power 1 over 4 here. Because after I do the differentiation, the number 1. Yeah, just people just don't want suddenly have a constant next to your stuff. It's just redundant, okay? Then you may also ask, will this half change the whole thing? No, because I'm only focusing on what kind of variable b will make this small. So the picture is like this. Suppose I want to find the minimum of x squared. Okay, what is the smallest value? 0, right? So this is x squared. What happens if I multiply half there? Then this curve looks like this, right? Everything go down. But it's still, what's the minimum? 0. And the same, if I divide this by 999, it may look like this. But still, this 0 is the smallest one. So that means what? That means if I want to minimize the f, it's the same as I minimize the constant times the f. This guy, it won't change the location of the solution, right? Therefore, I can put a half here so that when I take derivative, the 2 disappear. So this is the idea. So now after this I will change to what? 0.5 times this forbiddance norm square is small. Why there's a square? Because I want to do differentiation. If I don't have a square, then there will be square root. This is what we talked about last week, right? And then square root, we don't like to deal with square root. You can actually still work on this with a square root, but that's just make the math complicated. How I proceed? Well, very simple. I take the gradient of this thing with respect to b. I'm going to do is that b, this is my variable b. At the new iteration, I call it k plus 1. K is the step. I'm going to do the following. I will have my current variable b, okay? And then I subtract. Why? Because its gradient is n, so it's negative. And then I have a step size. I call it alpha, okay? Alpha k. And then I need to know this guy. that is the derivative of the f with respect to my current value of b. Okay, so basically it means I need to find this guy. Okay, this is the idea. Then you will ask, how do I find the gradient of this guy? So I want to find this here. Okay, so now I'm going to do it. So let me redo everything like what we did last week. Okay, so first, this is what? This is half, and then what? Trace, okay, of the thing inside, multiply inside transpose, right? So I have this two big bracket. Okay, what is this two big bracket? It's exactly the same thing inside. So I have x minus xab. Now, because I want to simplify notation, I'm going to call this thing j. Okay, so I have xjb. Okay, and then I have xjb. Okay, so I have half trace. So first, trace can go inside. Okay, so I will have x transpose, and then jb transpose. Okay, I just write jb, everything transpose. Okay, and then bracket, and then this thing stay there. I don't touch. Okay, and then I distribute inside. Okay, I should have 4 terms, right? So now what I will get, it will be trace, and then half here. I will have 4 terms. xtx, this is the first guy. xtx. Okay. Second guy xtjb. Okay, xtjb. Okay. Third guy, this guy is btjt, right? btjt. Then I have this btjtx. So btjtx. Okay. Lastly, we have btjtjb. Okay, plus btjtjb. Okay. Now we have this spectrum thing. Okay. Now what's next? I just need to make sure the trace is only on B. So you know trace can go inside, right? So I will have trace 4 trace. And since this guy have no B, I don't care. It's just a constant. So that means this guy in the end, I just write a C in the end. So I don't need to care about the notation. So now I have this big thing. And just recap, these two guys are the same guy because transpose. So I just need to care about this. I just ignore one of them, and then I just put a 2 here. Okay. So now what we have? What? Negative. The first thing, x transpose JB. Okay. What's the second guy? Second guy will be the half is there, right? So the half nobody cancel it. Okay. It will be trace what? B transpose J transpose. Okay. B, right? So I have this thing. Okay. Now I have this one. What's next? I write back J is my XA. It will be what? Negative trace X transpose X J. Okay. Okay. And then half trace what? B transpose B. So B transpose is the very beginning. Okay. And then the middle guy will be XA transpose XA. So it is A transpose X transpose X and then A B. Wow, very complicated. Okay. So now done. And then what? Plus a constant, which is actually transpose of A transpose A. Have no B, so we don't care. So now I have this. So how do I compute this thing? In the MATLAB is norm. Okay. So x minus x times a times b, right? So I don't have b, I don't have b, so let me make a b. Okay. R n. So bunch of number, just a bunch of number. Okay. So x times a times b, it will be just a bunch of number. And then I have x minus this is just a bunch of number, right? So this is what I have here. Okay. And then what I'm going to do is say norm. That means doing this 2 bar. Okay. It's called norm. But I need to specify what is the norm. You see, I can do flow. If I can also do 1, 2. These are different things. I'm going to do flow. Flow means 4 minutes. It's a name. It's a name. And I have what? I have 1 half square. So this thing I should square and then have a half, right? So I should have 0.5 in the beginning. Then I'm going to do this. Okay. Calculate this. It's a number. Okay. This is a number. So I call it f. Okay. I call it f. Okay. So now I have a number. What's next? I'm going to calculate the thing in below to see whether or not they are the same. Okay. So I'm going to do the following. Trace. Okay. Just type trace. Okay. And then what? Type this. X transpose x a b, right? Okay. Then x transpose times x times a times b. Yeah. And then there's a 2. There's a negative. Sorry. There's negative. And then what? This. Oh, this guy is very big. Okay. 0.5. And then time trace. And then what? Wow. This term is so big. Let me calculate later. Okay. Calculate this c first. This c will be half trace a transpose a. Okay. So it will be plus 0.5 times trace a transpose a. Okay. And then plus. And then you can have dot dot dot. It means next line. Okay. Next line is this guy. This big chunk of thing. B trans. Okay. So do it one by one. B transpose time a transpose time x transpose time x times a times b. Okay. Same number. Well, slightly not the same. Probably one of them have some numerical error. Okay. Slightly not the same. Okay. The issue is so clumsy. So therefore, people just type this. So this is what we have. So I have this. Now I'm going to find a gradient. So to find a gradient, this is a cheat sheet. This is called matrix codebook. So here you see, they give you a derivative of something with respect to a matrix. So we want to what? See trace. So you go down and now we see a bunch of formula. Okay. So what we have? Let me put it here. Okay. So what we have is this and this, right? So this is what? This is in the form of negative trace square bracket. This big chunk of thing is not B. Now I call it C. Okay. I just call it C. CB. Okay. Then this is our X here. Okay. This one. Okay. The notation is confusing, but here's the idea. This A is the C here. This X is our B. This B is identity, right? So we will get what? A transpose, B transpose, but the B here is identity. So we will get A transpose, so which is C. So this guy, if we take derivative, it will give us C transpose, okay? And what is the C here? It will be this guy transpose. So that means we will get this guy transpose, right? And since PQ multiplied together transpose is, you flip the order, right? Q transpose P transpose. So this is my P, this is my Q. So I will have A transpose, and then what? This guy transpose. This guy transpose is itself. So therefore, this. So therefore, this guy, if we take gradient, we get this. Okay? That means differentiation of this thing with respect to a matrix B give us. Now we look at this guy. You may wonder, okay, now I'm just looking at cheat sheet. How do you really get this later? I will have explained how do you really get this from definition and later. Now this, everything in the middle, I don't care. So I can say this is something like what? Trace B transpose Q B, right? Everything in the middle I call it Q. Then I just need to look at those that I just look like this. So it will be this, right? So this is X transpose BX, which is X transpose BX. So what's the derivative? It's BX and B transpose X. So that means the middle guy times my B and then times the transpose of the middle guy times B. So that means it will be QB plus Q transpose B. Okay? What's my Q? Q is this big thing called P this. So my first term is just this. Done. Then what about my second term? My second term will be the same thing, but this big thing, I need the transpose. Okay? So how do you proceed? This is a P, this is a Q. So I will have A transpose, this P thing transpose, right? And then I will say this is P, this is Q. So I will get what? Get this guy back. You see it? So this means these two guys are the same guy. So therefore, what I have, this guy, after I do the derivative, it is just this part 2 times. There will be 2, and the 2 cancel off with this. So we will get what? Plus this part. Okay? So it will be A transpose, X transpose, XAB. Okay, this is the gradient. Okay, after so many efforts, finally we get the gradient. So that means gradient of this function f, what we take with respect to b is equal to what? This thing plus this thing and like this. And these two things I can factor out, so I can even say that this is what? Identity plus, okay, this is minus. So it is minus plus AB, right? So now I get this. Let's call it. I will call it grad B, okay? What's the notation? A transpose X transpose X, okay? So now, because you see, I need so many X transpose X, I'm going to just name the following. XTX is X transpose X. So I don't need to type this anymore. I just type XTX, okay? A transpose times XTX, right? And then times what? Identity. Okay, so identity is called I, okay? EYE. EYE. But we need to know the size. So what's the size? The size will be how many, because this I is multiplying X, so it will be N, okay? M by N. So IN. Or I make this from the beginning. So now I'll make IN is this, okay? Then I will type here. IN, and this is minus, okay? And then A times B. So now I will get this. This is grad B, okay? Okay, I didn't define this. Okay, let me do it. Okay, now I should get grad B. Okay, okay, it's a matrix. So size of grad B should be the same as B. Yeah, because if I do gradient descent, these two guys are not the same size. How do they add them up? Okay, so what I have is now I have this, which I will clean the board. Okay, then go back to the very beginning. How do I minimize this thing? I just run a gradient descent using this. So what's the gradient descent? Let me recap. So I have my B, right? Then I'm going to minus what? Step size. I call it step size times my grad B. Then here's an issue. How do you find step size? At this moment, we don't know. So I'm telling you a magic trick. You just said it's 0.1. Yeah, you may say, oh my gosh, this is bad. Yes, this is bad. This is what you do when you don't know how to find step size. You first start with 0.1. If it doesn't work, you make the step size smaller. And if it also doesn't work, you make it smaller again. This is called line search. So I'm going to do the following. So let's see what I do. So suppose I do this, then I'm going to call this thing as my B temp, temporary. Okay. So I'm going to run this. Okay. Now I get a B temp. Okay. Now what's next? I need to check, is this guy good, right? How do I check? I check is if B temp is inside here, will FB temp smaller than FB? If FB temp is smaller than FB, that's what I want, right? I just want this guy to be as small as possible because that's what I said. I want this thing to be small. Then if FB temp is smaller, that's what I want, right? Then good. So I'm going to compute this thing. How do I compute this thing? This F thing, right? So I'm going to compute this on F. Okay, F temp. Let me call it F temp. So what's F temp? Everything is same. I just replace this by this, right? So now I compute this. Okay, it's 3.5 10 power 10. Okay, then I just need to look at what is this F. Okay, okay, I didn't compute it, so now I'll compute it again. Okay, so it should be correct because this is using B temp. This is using B. Okay, so now now we see a thing. What's the value of F? F is power 5. What's the value of F temp? Power 10. The function will go up. That means what? Step size too big. Okay, then what I'm going to do? I just put a 0 here. And then I do again. Okay. Let's see. Okay, power 8. Still, my f is 0.5, power 5. So, too big. Add more 0 here, okay? Oh, power 6. Still bad because I have power 5. So, I just add one more 0 here. Okay, then. Okay, power 4. Oh, good, done. Stop. So that means what? This B temp is already better than B. All the thing I just showed you here, this is a human coding. You should write it in a loop. I will do it soon. So what I'm doing here, what's the picture? Here's the picture. Imagine you are here. You are somehow at here. You are standing here. Okay? What is this step size thing? This step size is saying that along this direction, suppose this is the direction you move, how much you move. Firstly, I set 0.1, right? It turns out after you move here, you go to here. The function value increase, right? Previously, you remember, right? So that means this amount is bad. Then what you do? You make it shorter. Shorter in my implementation means divided by 10, right? So now you try again. Oh, it turns out you are here. So you're still going up. It's not good. Then I make it shorter again. Then it's here. Not good. So what's the whole picture? The whole picture is, okay, you don't know where to go. You just know go this direction. So first you reach here. No, this is not good. So then what? You reach here. So no, this is not good. Then you reach here. No, this is not good. But somehow when you make it shorter, it go down. So that means what? That means probably maybe the whole picture looks like this. Then of course if you move this much, you go to here. But if you move this much, you go down. And what we want to do is go down, right? So that's how you do it. This is called line search, and this is the most naive, easy, simple way you go down. There is actually a formula for you to find this, but I'm telling you this because this always works. This is the most stupid method, but this always works, so worth learning. So how do you code this? So here's how I code it. F temp equal infinity. And then what? Wow, F temp is larger than F. I do think I make my step size too small. That's it. So I will have my step size originally is 1. Okay. And then what? While this is true, I make my step size divide by 10. Right? And then what? I repeat this. Then eventually it will have a step size that is small enough that I will go down. That's the idea. So I do this, and then now I will put this here. So now let's see. Okay. Okay. Let's make setting as okay, done. Okay, good. Now see. So what happened here? I search 3 times. First time, power 10 is like too big step size, not good. Second time, this is going down, so it probably is now here, still too big. Third time, here probably is here, is above you, not good. Last time, oh, go down. So this is not much because our original f function is power 5. So in this picture, it probably means we go to here. Okay, got the picture, right? So that means what? That means when you are doing optimization, you are actually in a dark place. You don't know the surrounding. So that's why you don't know the step size. You're in the dark place. Yeah, this is a very important understanding. Okay, now good. So I'm going to code this. So how do I code this? So I'm going to repeat this many times. So here's how I'm going to do. After this while loop, that means after this end, that means everything is nice, right? Then I will say this is now my B. Yeah. Then I'm just going to repeat this many times, including computing the B. Then I'm just saying, okay, what I'm going to do, for iter equal to 1 to 10, let's say I do run 10 steps, this, okay? And then what? Every time when I finish this, I will compute the value of my B, which is the f temp, right? So my f iter, iteration, iter will be my f temp, right? Because after this step, this is the value that makes function value ground. So I store this. After I have this, my f is f temp. I'm saying in the new iteration, I need to be better than the previous version. So I'm now going to run everything from scratch. Okay, run this. Okay, this is value. Now I get the plot that looks like this. It's correct. It's always going down. Okay, now just some MATLAB thing, how to plot this better. So this is MATLAB. Okay, this is not good. So you should do the following. For example, first you should line width. This is too thin. Maybe hard to read. I add this. Let's see what happens if I do this. Okay, now. Okay, L-I-N-E-W. Okay, I make a spelling mistake. Okay. Okay, now see thicker, right? But still, it's not good. Why? You cannot see which iteration is which iteration. So usually, first I will use dark. K means black. B is blue. Okay, so now this becomes black, and then I will write hyphen and then have an X. That means I mark the point. Now you see a bunch of small cross here, but this is still too small. So I will do the following: marker size, make it 10. So I do this. Now you see these are cross. You see the location. And then what's next? I'm going to do what? Grid on. Because this, now I have a grid here. And then these are too small. So you set the following. Set GCA, get current figure, font size. Yeah, make it 25. Then once you type it, boom, nice. Oh, this is too big because you only show two things. Then I make it smaller. Let's say 20. Oh, now this looks much nicer. Or maybe it's still too big. Make it 17. Okay. Good. Okay. Now suppose I do some reason I want the line to be dotted line. Then you change this to this. Okay. Then let's see what happens. Okay. Now you see it's a dotted line. This is useful when you have more than one line. If you plot 5 curves and they are all solid line, they block each other. So you need this. Or you can say you have broken line like this. Let's see what happens. Okay, you see that, right? But for now, we only have one line, so I can just do this. Okay. And this is X, right? You can also do something else. For example, I put a plus here, then it becomes plus. Okay. But for this part, this is good for some reason. Why? This part is almost flat, so the plus sign will indicate very clearly where is the location. Okay. And of course, you can do something else. For example, you can type a V here. What happened? Let's see. Then it becomes a triangle. Okay. And then you have other symbol. Okay. Then this is one thing. And then what's next? Well, this is in linear scale. What if you look at the y coordinate here? This is very big jump. These are very small because they are in a magnitude much smaller than this. So how do I make the plot better? Semi-log y. I make the y in log scale. Let's see what happens. Okay, now you see y-axis are in log scale. Okay, so this is slightly better. If I don't do this, this first iteration take up all the space and you cannot tell what's happening here. Because it's possible. Actually, it goes up, right? We don't know. But if you make the scale better, this is now better. But still, you cannot see. If I have 100 iterations, in the end, same thing happened, right? So here's another trick. I'm going to do the what? F min. The smallest possible value I can get in the whole iteration. So, which is 50 something. Okay, I'm going to what? Minus this with all this value. So that means I'm forcing the last guy to be 0. And let's see what happens if I do this. Suddenly, it's very clear. Because why? Actually, and you suddenly found that, oh, the last guy disappeared. Why? Because the last guy is literally 0. Log 0 is error. Log 0 is negative infinity. So that's why you can show it. But now you can see it's going down like a straight line. You can even say it's a straight line. So you can even tell how fast it converges. For the first 5 iterations, every 2 iterations dropped the error 100 times. After here, it got stuck. Okay, but anyway, you see. But this is not possible previously, right? You see previously, I cannot see this. So remember this, okay? This is very important. Okay. Then now what? This is how many iterations? 10, right? Let's say we run it 50 times and run everything from scratch. Okay. So you jump up. Now you see this. Okay. So now this is the behavior of 50 iterations. That means it is very fast in the first 5 iterations and then it got stuck. This simple code is telling you what? How to what? Run gradient descent. Then now, what about if we have constraint? So now let me add constraint. Okay. So let's say I want to minimize this. Okay. And in our discussion 2 weeks ago, we said that b had to be larger than 0, right? Then now I have this. So I want to make sure red is true. This thing is possible. I subtract too much and make it negative, right? Then it's not larger than 0. Then what I do? I project it back to the Q. Okay, this is what I talked about last time in the video. I have a Q. I have to minimize. This is what I talked about. X inside set Q, which is this is the legal region. If outside this Q, everything is illegal. So what I'm going to do, very simple. If doing the black gradient descent, stay within the Q, I do nothing. But if the X leave outside the Q, I go inside Q again. And for our Q means larger than 0, then the projection for this particular case is just max it with 0. So I'm going to do what? Max 0. Okay. Now instead of 500 iterations, let's say I do 50 iterations. I just add a new step. Let's see, I run this again. Okay. I still get the same figure. Is all the b negative or non-negative? That means larger than 0. Let's see. I type a b here. Yeah, you do not see negative number. You see? The smallest one you see is 0. So therefore, that means what? How do you solve a general optimization problem? You need to know 3 things. This is a general optimization problem. You have a general f. I didn't specify what's the f. You have a q, a general q. I didn't specify what's a q. How to proceed? You need 3 things. Number 1, how do you know the gradient? Number 2, how do you find the step size? Now you should know. You can do this line search thing. If the step size is too big, drop it. Okay. How do you find this? Either you calculate by hand from definition or you check data book. Okay. This part is the tricky one. This part is tricky. I just said that for b larger than 0, this PQ thing is just max. But for what we discussed 2 weeks ago, we have the following. This one is difficult, okay? We have this. We have to minimize a function f. Let me now call it a vector x, okay? We have the following thing. We have x larger than 0 and what? All the xi, some smaller than 1, right? A vector point need to be inside a simplex, right? For 3-dimensional case, you remember, this triangle is the boundary. You cannot leave this triangle, right? Because leaving this triangle means some of the entry is larger than 1 and some other entry is more than 0. For example, if you move in this direction, okay, then this coordinate is negative, right? So for your problem, you have this thing. So that means you need to know how to project onto this triangle, okay? This is what we discuss next week. This part is easy. It's just max with 0. This part is not easy. This part is what we discuss next week.